right. Our section 4.8 has to do with Newton's method. I was talking with some people before this, and I don't have anything up as far as the Tada way of doing this. So I've never found a really solid way of approaching this topic, because it turns out that once you understand the mathematics behind it, it's really a fun topic. But I bring in not only the mathematics, I bring in some graduate stuff I did with the calculator to do some Feigenbaum numbers that you have nothing to know about. Yeah, anyway, so I took that topic from grad school. Grizz is out already. Hey, Grizz. And I took that topic along with your linear approximation topic that you had already, how you doing, a while back, and I'm going to try to go after Newton's method, okay? Newton's method is a way of coming up with solutions to problems based on an iteration, okay? And you're going to say, what's an iteration? You're trying to solve something, and you're using an iteration to do that. An iteration means that you start off with a guess, a good guess, a guess that's reasonable and close. If your guess isn't reasonable and close, your iterations will take you far away from the solution. So you take that guess and you run it through an idea you've set up. And that gives you a better guess. And then that guess gets run through again, whatever you've set up, to give you a better guess. And how you tell these guesses are the best? Well, you start comparing the decimal values. Once one guess has 2 decimal approximation accurate with the third answer, then you know you got the first 2 decimals right. Once you have the 4 and 5 decimal places matching up with your guesses, then you know you're really close. And every iteration you can tell is by using, well, your first guess is you type it in and you press enter, and then you press enter and enter and enter. What I'm about to show you isn't in the calculus book for the iteration. It is in the calculus book for Newton's method, so some of this is in there and some of this isn't in there. Once you see it, don't lose it until after June, because it comes back up in your final exam. So it's kind of neat, and you can't program it. But anyway, I'm going to go back to do the linear approximations. I'm going to go back to this topic first, okay? So this topic on linear approximation, do you remember what we used it for way back when? Right, we found the square root of, say, 26, okay? You want to find the square root of 26. So we said that was approximately equal to, and we said f of x equal to square root of x, okay? We took the derivative of our guess. We said x1 equaled 25, and we said delta x equaled 1, okay? So square root of 26, we said was close to the derivative, 1/2, 25, negative 1/2, times delta x, which is 1, plus my original value, the square root of 25, okay? And we used that, and that was hard enough to remember how that worked, okay? And we said that was a linear approximation, and we came up with, just because 1/10 plus 5, 5 1/10, okay? Fantastic. So we said the square root of 26 was close to 5 1/10. Well, that was good for then, because we realized that on the square root, if this is 25, this is 26, and we used this line to approximate that function value right there, okay? They're close. Well, obviously, my graph is not accurate as far as the width between the two, but it's close. So using the right side of this, I was able to approximate the actual square root of 26, okay? So I approximated it. What Newton came up with was he wanted something better than just 5 1/10. Now remember, they didn't have graphing calculators. They didn't have a place to go get the answers. They had to grind these out on their own. So when they went to work that morning, they could spend all morning just working on getting one answer, the accuracy of one answer. So this was built for speed and efficiency. And it was built as a way of coming up with answers to questions that most people couldn't answer. So in taking this, I still haven't come up with a good way of doing this, but I'm going to give it a go. In taking this idea, and we all realize it's pretty close. It's something you can do in your head without a calculator if you had to. And we had to. So I'll move that out of the way because I was hoping this was checked. There we go. All right. So if I take f of x sub 2 and subtract over the f of x sub 1. Okay? Now f of x sub 2, this is approximately equal to the derivative of f of x sub 1 times delta x. Okay? I got some other things going here. All right. F of x sub 2. That's like f of x sub 1 plus delta x, isn't it? Like we had 25 plus 1 gave us 26, right? And we subtracted f of x sub 1. That's getting close to something. Oh, and delta x, that's x sub 1 minus x sub 2. F prime of x sub 1 times x sub 2 minus x sub 1. That's kind of like what that is. Anyway, what we got to do is we got to get to Newton's method somehow with our guess. Which one's our guess? X sub 1 is our guess, isn't it? And this would be our result for our iteration. Okay, so x sub 1 is our guess. I need something that comes out with, wait a minute, I have another screen here. Ooh, that doesn't look very good. Does that look very good? That looks all right. What? I know it is. The problem is there's one big missing link right there. The zero. The zero. Someplace it will equal 0. Wait a minute. Maybe Newton's method approximates the zeros of the function, thereby giving me a value set equal to 0. Maybe that's the key. Maybe that's the trick. That'd be interesting. So maybe you can only use this for zeros of functions. If you did do that, if you approximated that x sub 1, ran through the derivative and got x sub 2, and if you ran that through the derivative and that through the derivative, maybe it would work. You want to try it? I don't either. I don't know. Like Sam said, we got what? What's our first question we have for homework? Or is it Alex? The cube root of 2. It's supposed to be our first problem. We have to approximate the cube root of 2. So if I take f of x sub 2, if I change it into f prime of x sub 1, no, not yet. Don't erase it. No. Why would you erase it?
Because I didn't know if you were doing it.
Well, the change. Yeah, that's it. Newton's method has to approximate the zeros of the function. So, in order for this to equal 0, you have to subtract it from itself. Nice. Well, sure. Yeah, they do. If I want to approximate a 0,
Why
Oh, because I know, and all the random helps. If you want to approximate something equal to 0, and you want an equation that does that, say you have this, okay? Say you want to approximate that. If you have these derivatives that go through and approximate it, they'll get you closer and closer using the tangent line. For instance, if I want to approximate this 0 of an equation, I have to take my answer, and this is the equation of something that equals 0, right? What is this the answer to? It's the answer to the problem of x minus the cube root of 2 equals 0, right? It's also the answer to x equals the cube root of 2. It's also the answer to x cubed equals 2. It's also the answer to x cubed minus 2 equals 0. It's the answer to all that stuff. To use Newton's method, we have to use the one that you can take the derivative most easily with and make a guess of to work with. I would say it's going to be that one. You can take the derivative of x cubed pretty easy. 2 is a nice whole number. If I can pick any one of those, but for Newton's method, I have to pick the one that equals 0 and will allow me to get that approximation. So my first guess will be close. If I'm going to approximate equals 0, that's the key to the whole problem. I was using it to just approximate anything. I forgot it had to equal 0. If that's true, then I can subtract this over this negative f of x sub 1. That's still approximately equal to the derivative of x sub 1 times delta x. Right? Yeah.
So are we down the other side of each of these ones?
Well, don't ignore it because I think that comes up later in the next chapter. I think I got the two sections mixed up.
So
This is Newton's method, I think, because we're approximating zeros of a polynomial. Zeros of a function.
So could we just not use f of x sub 2?
Well, watch this. I'm not trying to find f of x sub 2 because we know in math that wherever it crosses, what's the y value of that crossing point? 0. So if I pick a number, say x sub 1, and it comes up right here, the tangent line will get me close to that point. So I'm trying to approximate the x value of when y will equal 0 in the polynomial. Yeah, and I divide f prime of x sub 1, f prime of x sub 1. So I have the opposite of the function value of sub 1 over the derivative value of x sub 1. That's approximately equal to delta x. And we said earlier x sub 1 was my guess, right? And delta x is the difference between my next one and my guess. How you doing? That's oh nah. What? Man. Negative f of x sub 1 over f prime of x sub 1. All right? I think we almost got it. Easy. Newton's method. Yeah, it's right here. We took f of x sub 2, f prime of x sub 1. No, you're going to watch for just a minute. You're going to do it quietly, plus f of x sub 1. We took that linear approximation, which was good for one number, one run, and we turned it into the zeros of a polynomial, or any function, and we got x sub 1 minus f of x sub 1 over f prime of x sub 1 is approximately equal to x sub 2. Notice it doesn't equal a y value, but it equals an x value. Okay? So going back to this, the cube root of 2, we're almost there. For Newton's method, we want to go to the zeros of a polynomial. We already said x cubed minus 2 equals 0 would work. So if x cubed minus 2 equals 0 is what we're going to work with, we have two things. The function value is x cubed minus 2, and the derivative is what? 3x squared. Now I've got everything I need. I've got my initial guess. I don't know, my initial guess is 1. Does that sound good? 1? Sure. Let's say let x of 1 equal 1. So I have 1 minus the function value of 1.
Where did you get that? Or just us?
Well, what else do you want to pick?
I didn't know if it mattered or not.
Well, I'm not going to pick like 12. The cube root of 2, it's got to be 1 point something, doesn't it? Yeah, something close. Right. Now remember, if you guess wrong, off you go. If you guess right, there you go, right there. But anyway, if I put 1 in here, 1 minus the function value of 1 is negative 1. And the derivative is going to be 3. So it's going to be close to 4/3, right? 4/3. This is where Newton's method differs from the linear approximation we started with. With the linear approximation, we are done. With Newton's method, I can keep going. Now I can put 4/3 minus the function value of 4/3 over the derivative value of 4/3. And this is where people start getting a little testy. I'm like, and they go, how do you know when to stop? I go, you know when to stop when you're done. Oh, can you just imagine? I said, now wait a minute. I used a calculator for an iteration before, and I showed you last year on the calculator how to do an iteration for this very moment. Do you remember how to do an iteration? Oh, you do so. You start off by going, this doesn't solve the problem, so those of you who instantly want the answer right now, you're going to have to wait. This is simply how to do an iteration. If you want to do 5, press enter. I want to go up by 5. Yeah. Plus 5. Then you press enter. 10, enter. 15, enter. 20, 25, 30, 35, 40. And you get the iterations. That's an iteration. You set something up to crank out these numbers that you run through your rule of answer plus 5. Okay? Very good. So, what we need is our equations. Y equals x cubed minus 2. That's my function. X caret 3 minus 2. My derivative was 3x squared, wasn't it? 3x squared. Right? Those are my derivatives. Fantastic. Second quit. Following Newton's method, I chose 1 for my initial value, x. 1 store x. Store is over here on the left, second from the bottom, right above on. I'll press enter. Now, Newton's method is so slick and compact. X minus bars, y bars, function, y1, parentheses, x, not 1, x, divided by my derivative. Bars, y bars, function, y2, parentheses, x. Oh my gosh, is there another way? Come on. Your finger can't be getting that tired. It's not that difficult. What's going to happen when I hit enter? I should get what? That is my first iteration. It's very important you understand because on the test I'm going to say, give me your answer after 3 iterations because I know you know how to punch out the cube root of 2. So this is the first iteration, right? I'm going to press enter and this is the second iteration. Oh! Sorry? Slight snafu there. Yeah. 1, enter. Forgot the answer. Ready? Second answer. Minus bars, y bars, function, y1, parentheses. Second answer. Whew. Good thing Rachel's not here to bars. Wait a minute, she's listening, isn't she? Function, y2, and answer again. That was how Feigenbaum worked. I used my answer. There we go. All right, looking good, 4/3. Now I'm going to take my answer, run it through again. 1.26. 1.2599. Wait a minute. I have 1 decimal of accuracy now. After 3 iterations. Now I have, 3, 4 decimals of accuracy. 1.2599. See how it works? It is crunching this out so tight, so quickly. Now, right there, I got 8 iterations. I got 8 accuracy. Now, I would have you stop probably on the second or third one. Why? Well, because it's no fun just to take your calculator and go to math, 4, 2, cough and scoff at the question and write down. See it? That's no fun. That doesn't let me know if you know the mathematics behind how the calculator works. I want to know this answer. Why? Don't you want to know the right answer? That is the right answer if I ask for 2 iterations. Anybody can just do that. But you guys have style now. You can do it without a calculator. It did. Woo-woo. That wasn't so bad. And it didn't take me 40 minutes. That was question number 1. We approximated the roots of a polynomial without using 0, calculator, a solver, but we used calculus to do so. Yes? 1.2599.
So you still want the third one?
She said 4 decimal places.
No, I mean.
But like those around 4 decimal.
Oh yeah, you just write down all 3 as your answer. You show me the pattern that you got there with. And it's not going to take that many because this is a very strong method. In fact, it's theorized this is the thing that's in your calculator right now to run these problems.
But they say that?
Nobody ever really shows or tips their programming hand. But if I was going to program how to find the zeros of a polynomial, Newton's method would be in there somewhere because it works so fast. Haven't you ever wondered why you had to have a guess on the graph to start your bzzz? That's what you're doing is you're starting.
Don't just scan.
Right. It doesn't, it's not, the visual image is just for you. The calculator doesn't use that in any way. It's just for you to see what's happening. It's using this, and it does it 10 or 12 times, gives you the answer because in 10 or 12 times, it's going to hit there no matter what. As long as it has a guess that you've given it that's close. Okay? Yeah.
So would you round the second one up if it's 4 decimal places?
No, I'd just truncate it. I'd cut it off.
Why do you think it equals 1?
That is, if you come in without a calculator, that's how it starts.
You really don't have to do any of that if you don't, and you have a calculator.
Right, but if you don't, I can say, oh, we did it manually in class, so you're fine. You're just going to, it's going to take you a little bit of while to do it. Okay?
So we don't just work calculator?
The work that you show is going to be what function did you use, what derivative did you use,
Yeah.
and what x1 did you use. Huh?
Why did you choose X?
Oh, because I wanted something that I could easily take the derivative of, something that I could easily guess, and something that equaled 0. Those are all critical points for Newton's method.
When you plug in for X1, would you use whatever number you want?
As long as you're close. If those guesses start getting away, change your guess and try it again. Okay?
Why do you get a different answer when you plug in 1 in the calculator and then when you plug in the answer?
Because when I plugged in 1, the calculator stayed at 1. When I plugged in answer, it allowed it to put in the last calculation, which wasn't 1. Okay? I simply went to second and negative and typed in
Oh,
A and S as my variable. Now here's a real nifty part. For our next problem, I don't know, what's the next problem? Give me a problem, Sam. Give me number 2.
what about number 3?
Number 2 is what? Fifth root of 3. We're going to approximate that to apparently 4 decimal places. Okay. Now that you've seen that we want zeros of a polynomial, it's pretty easy to see that this is going to equal x. 3 is equal to x to the 5th. 0 is going to equal x to the 5th minus 3. Okay? So that becomes my function, f of x, equals x to the 5th minus 3. And my derivative isn't too far off. It's going to go 5x to the 4th. Okay? So the nice thing about this is if I go to y equals, I just have to type in my new function, x caret 5 minus 3. And I type in my derivative, 5x caret 4. Now I simply do I don't know, what do you think the fifth root of 3 is close to? 2, 1, 1.5? You want to do 1 point, or just 1? All right, 1. And now I can do a recall, second and enter, second and enter, second and enter, and there it is. I've changed the y1. I've changed the y2. I put in 1 as my answer. I'm ready to go.
Wait, I thought we were like.
No, that was when we were putting in for x. And since we're putting in for answer, there's nothing to store because answer automatically picks up the last thing calculated. Okay? That's why I just typed in 1 to get started. If I wouldn't have done that, it would have picked 1.25. Just whatever. Now this line will stay the same. In fact, some people play a mean practical joke on other people, and I can tell when they take the test, because they get to this question on the test like, oh, somebody cleared out their calculator, and they didn't know it, and that line was missing. They're like, what was the line? It was in there. Somebody hit a bunch of zeros and enter and cleaned it out. Okay. I thought it was pretty funny. I guess you had to be there, which I was. I also saw Lewis, remember? I was on the way. Hey, Lewis, what are you up to? We're close. 1.24. Yeah, 1.2457. So you're getting the benefits of using Newton's method for solving these. You're also getting a little bit more insight on how the calculator does it and why you have to give it a guess that's close. Okay? You write down well, you can write down your pattern and then stop right here because you have 4 decimal places of accuracy right there, 1.457. Because it matches, this confirms it right here. Okay?
So when you get one that matches.
The one above it,
Yeah.
that's where you stop. So this would have been 1, 2, 3, 4 iterations. Okay? Because you had your original guess of 1, which doesn't count. You pressed enter to get this iteration. That's 4 iterations. Okay? The safest thing to do on the test is just to write down your lines of output. How you doing, Chris? There you go. All right?
So if we don't know a guess, can we just type in our calculator and then put in one number that's closest to it?
Sure. But there's got to be something involving trig, doesn't there?
Are you saying that they're going to put signs in this or something?
Well, I don't know. I was going to ask Sam. All right, because I don't have anything written down for just probably doing problems.
How about we do one like the next one? Like
No.
the next one.
All right, we'll get number 6. Right, you don't have to write the end. All right, we'll do number 6.
Sine of x. Number 1 plus x log of x equals cosine of x.
Oh, jeez.
And it gives a domain of 0, 1.
Well, obviously, it wants the answer between 0 and 1. So the polynomial aspect of Newton's method is out. But I say it still calculates at zeros. So they're given the equation to do that with. Let's give it a whirl. What do you say? Sine of x plus x cosine of x minus cosine of x equals 0. Now, I'm surprised nobody's saying anything yet, but I'll go ahead and say it now. Edit, view, hide. No, I subtracted it, said equals 0. All right, so there's a way to make this easier. Nobody has brought it up yet, so I guess I'll sine of x. I'm not going to type it out twice. Plus x cosine of x. What? If it was squared, yes. Sine squared plus cosine squared equal 1. Minus cosine of x. And you have inner math in derivative bars, y bars, function. It'll do the numerical derivative. That's what I want. I want numbers. Math 9. We've done that before, numerical derivative. Okay.
You only don't know what to do. Math 9, you said?
Yeah, math 9 gives me the numerical derivative of y1.
Can you come in, look at this?
Comma x.
Yeah, because x is your variable and x is your input, and x comes from your graph.
D of x, y1, x equals x.
No.
Is it in derivative?
Yeah.
It's 8.
And then down.
Yeah, that'd be x.
That's what I got.
That'd be y1.
Yeah.
What? What am I supposed to put for this?
Is it x equals x? First part right
E.
here. Yeah, because
Yeah.
x.
Right.
No,
Yeah, I
mine
have
is
that
doing
on
that too.
I didn't find in derivative.
That's x. That's y1.
Huh?
No.
And that's x.
Okay, can you do that?
Will it stay like that now?
She can.
Do you guys have like a box? That's what they have.
Wait,
Mine never really stopped.
Math
until it was
9?
0. Math 8. I had math 8.
I am not graphing it.
Oh, I didn't graph it
like
either.
that?
Yeah.
Over the end. And then what do you fill in?
It just kept changing until it got to 0, and then it stopped changing.
Nice. Second and quit. All right. What number is this? 6.
Pause while I write this down. Yeah, we can go.
Pause? Sure.
Are
'Cause
we
all-
equal one again?
Huh?
Are we equal one again?
No. We have to pick a number between 0 and 1. And based on your experience in graphing, what would you pick? 0.5. It's in between 0 and 1.
Get an arrow.
What?
What's the exact middle?
I don't know. 0.5. Now, what mode do you have to be in also? Radians? I'd say it's locked in at 0.47973, wouldn't you?
Yep.
You did not?
I got that.
Mine changes like crazy.
What did you pick as your entry?
0.5
Are you in radians or degrees?
radians.
Tell me zero.
Mine just
Get an
goes.
error.
I got it.
I got
And it's supposed to be in
7, 8.
Supposed to be in radians.
Are all of this supposed to be in radians or just for this thing?
Every single problem. And you didn't get that.
Oh wait, do we
I
have to
get
do
this.
answer in our derivative? Oh, that's or x. That's what I did.
Answer.
No, I mean in your
No, x.
y equals.
Did anybody else get this or am I way off?
I got it.
Ooh. All right.
What did we do wrong?
Inputted it wrong somehow?
I used the same one that I used before.
Let me see the calculator. No, it's okay.
Okay. How is what I borrowed?
0.5.
No, I can remember.
Sine of x. You got 3 in derivatives. Sine of
Yeah,
x.
but it's only using y2. It must have been close.
Math.
Oh, that's enough.
Comma x, comma x. All right, sine of x.
Oh, that was big.
You would go to my desk at all.
Now, your equal sign wasn't highlighted, so I highlighted it. And it did go to 0. Oh, because you got y1 and no, y1, y2. I don't know. Interesting. You have to figure it out.
So, Mr. Barons, what do you want me to do about it?
I don't know. Research it, I guess. Yeah.
For that y2, where we just have it like the end derivative, can we do that even when we do polynomials?
Probably. Yeah. All right. Oh, how do we know if we're right? Glad you asked. Because I'll just go check. Instructor salute. I did do that. Chapter 4?
C, 4.8.
4.8? Number which one? This was the best thing I did was ever scan these books. 4.9? Six. 3, 4. Hey, 0.4797. So we're in pretty good shape. All right. So I think the homework isn't very long today because I'm going to walk around and debug some calculators, if I remember correctly.
What are you doing for a calculator?
Some of them aren't working, so I'm going to walk around and take a look at them while the other people start their homework. And the homework, the internet's been acting up a little bit. That's why I have, yeah, you definitely want to try it.
We can do all the homework wrong in the last.
Luckily, I have a backup copy here. Yeah, it is. It's loading. Well, I know, but now I got an hourglass. It should go, shouldn't it? There. Yeah, 1 through 5 odd. Well, I gotta walk around and check out some calculators. And a lot of people haven't even done one of these yet. Let's see, recording. Oh, I need to stop it. Okay, Rachel, there you go.